So, question 5, we're looking at, by restricting f of x to a monotonic increasing domain, find the inverse function of f of x equals x squared plus 1. So, jumping over to Desmos again, so this is the curve, or the function x squared plus 1, and we can see that it's not monotonic increasing. Here the function is decreasing down to the vertex, and then obviously increasing again. Super important when we're asked to find inverses of any parabola. The key is to find the vertex. Can't do anything without doing that, but this one's quite an easy one. We don't just know the vertex is shifted up here to 0, 1. But again, like obviously this parabola fails the horizontal line test, which means that as it currently is, we cannot find an inverse function. We can find, just as like to go a little bit further, we can find an inverse relation. We could just throw this thing on its side, reflect it all in the line y equals x, and this is what we call the inverse relation. But obviously, because this red curve fails the vertical line test, it's not a function. Okay, so hopefully that makes sense. We can do an inverse relation of this thing, but we're looking at an inverse function, so it's no use to us, so I'll get rid of it there. So what we need to do, because we can only find, and this isn't a one-to-one function as well, because this two x values here share the same y value, so it's not a one-to-one function. So what we need to do is restrict the domain. Look, we could restrict it to monotonic decreasing or increasing. It doesn't tell us, it does tell us to restrict it to monotonic increasing over here. So that's nice and easy. We can see that it's going to be monotonic increasing to the right of the vertex here. So we can do that in Desmos by just restricting it to where x is greater than or equal to 0. And then that's going to, oops, don't need that, just need the curly ones, there we go. So now we've restricted this function to its monotonic increasing half. So now we can find the inverse of it. So we'll do this, we're going to do it again, we're going to do it both ways just while we're sort of learning here. So we are starting with the curve y equals x squared plus 1. So to find the inverse function, we're going to start by switching the x's and y's, and we should, very important actually, stating the domain here. This is for where x is greater than or equal to 0, and the range y is greater than or equal to 1. Just jumping back over here, y is greater than or equal to 1. So really important. So when we jump over and we're going to switch our x's and y's, x equals y squared plus 1. And now again we're swapping our x's and y's here. So our domain takes on this property. X is greater than or equal to 1. And our range takes on the original function's x. So it's just like that. Like I said, we swapped both of them over, just like we swapped the x's and y's here. So then we're going to be y squared equals x minus 1, working to make y the subject. So y equals plus or minus root x minus 1. But because we're thinking, we've got to, it's got to be in this domain here. We know that y has to be the positive branch. We know that the surd part's always going to deliver us 0 or a positive number. So in this scenario, we're taking just the positive version of root x minus 1, because we are at this domain and this range. So this is the only part of it that fits our solution. So here's our inverse function. And again, because this is quite a simple inverse to find, it's not too hard for us to then go through and start doing part B of the finding the derivative of this inverse. So y equals x minus 1 to the half. So differentiating here, 1/2 x minus 1 to the negative a half, which goes down into 1 on 2 root x minus 1. Perfect. So, but again, we'll just do the alternative way that's going to be, the derivative of the inverse function. Another way that will help us in part C. As I said, I think this is what they've asked for part B, so we're happy with that. But the other way to get the same result that's going to help us in part C is, again, just to start. I didn't do the inverse derivative of the inverse in white, sorry. But if we start again by the original function y equals x squared plus 1, we start by x equals y squared plus 1. Now we start by doing dx dy here is 2y. So that means that the derivative of the inverse dy dx is going to be 1 over dx dy. So another expression for the derivative of the inverse is going to be 1 over 2y. Okay, so we've got two expressions for the derivative of our inverse. This is expression 1, the derivative of the inverse in terms of x. And here we've also got an expression for the derivative of the inverse in terms of y. So we'll talk about what's going to happen here in part C. So part C is asking us, given that 5, 2 lies on the inverse, so let's just come back over here, double check what that looks like. X equals f of y. So now that's been restricted for us as well, the inverse. Moving over. Here we go. Here's the point 5, 2. Again, it's nice and easy to see. Again, if we just throw line y equals x, this inverse function here in the blue is this original function here, reflected over the line y equals x. The point that was up here at 5, 2, been translated over to, was at 2, 5, translated over to 5, 2, so switching the x's and y's. 0, 1 is translated over to 1, 0. And everything else here, the point 1, 2 has shifted over to 2, 1. So it's, again, everything in inverse functions is just swapping that x and y value. So we're looking for the gradient of the tangent out here. Did they ask us to find the equation? No, they're just asking for the gradient. So again, two ways to do part C. So for part C, the gradient of the tangent at 5, 2. So using this method here, using this derivative in terms of the x, 1 over 2 root 5 minus 1. Well, that's 1 over 2 times 2 it ends up being, which ends up being 1/4. So that's the first way to find the gradient of the tangent using this expression for the derivative. And we also could have done it just as simply at the point 5, 2, using the y value and subbing it in here, dy dx, or the gradient of the tangent I should have put actually, to keep it the same as over here, but it's the same thing, 1 over 2 times the y value of 2, which equals 1 over 4. So again, we're getting the same result either way. The thing that's going to determine it for you as we move on to harder examples is what's going to be easiest. This way is going to be often easiest algebraically. It's just whether they ask you to find the inverse function first. Because they did that over here, it might have been better to keep going this way. I hope that bit makes sense. Let me know if you have any questions at all about that. Let me double check that we've answered everything. Yep, gradient of the tangent at that point. If you wanted to go a step further, and find the actual equation of the tangent at that point, we could go, y equal, y minus y1, which is 2, equals 1/4 x minus 5. So then 4y minus 2 equals x minus 5, 4y minus 8, x minus 5, so we'll go x minus 4y plus in the 8 over gives us plus 3. equals 0 is the equation of the tangent at that point on the inverse. So let's throw that in here, just double check. X minus 4y plus 3 equals 0. And there we are, perfect. Okay, so equation of the tangent at that point, 5, 2. Always nice, I think, obviously your answers are there in the book as well, but doing all this makes you check and visualize exactly what's happening and whether you're right or not. So yeah, if you can do that, I reckon it'll put you well ahead. Awesome, thanks so much. Let me know if you've got any questions.